Okay, then we'll start. So, in power plant, basically, it is a very important topic, and first of all, and it will contain roughly around 4 to 6 marks in your gate paper. The syllabus first, I will tell you what is the syllabus and what are the important topics which you need to cover. Uh, First, first topic which is very important in power plant engineering is simple gas turbine. Simple gas turbine. And second one is the Rankine cycle. These two topics are very important uh, for gate. These two topics will cover roughly around 4 to 6 marks, and this is the weightage mostly you will get for the power plant engineering. The other part which is also there in this is compressor, which we will discuss in short because I haven't seen any questions of it frequently. The first two topics are very important. So we'll start with the this gas turbine only. So first of all, can anyone tell me what is a engine? Hello.
Uh, Engine is a device that converts one form of energy into mechanical energy.
Heat energy into mechanical energy.
Okay. Okay. It Yeah, you are right. Engine is a device which converts one form of energy into another form of energy. So basically, there are two types of engine which we normally see. First one is the IC engine, and the second one is external combustion engines. The one which we see in our automobiles are IC engine, and the one which today we are going to talk about is the external combustion engine. So, what is the basically the difference between the IC engine and external combustion engine? Is that in internal combustion engine, both compression and expansion of the working fluid takes place inside the at same location, that is inside the that cylinder, whereas in a external combustion engine, compression takes place at different position, whereas expansion takes place at another position. So both the compression and expansion are not taking place at the same time. That's at the different places. That's why we call that gas turbine as a external combustion engine. So we'll write some notes regarding internal and external combustion engine, that both compression. My handwriting is not good, so please deal with it. And expansion occurs at same location, whereas in external combustion engine, compression occurs at different compression and expansion both at one location. You can say one location, and expansion occurs at other location. Okay, so this is the basic difference, and uh, uh, now we can easily differentiate between internal and external combustion. Based on this, we can determine the what are the advantages of the external combustion, or you can say gas turbine, over the internal combustion engine. The first advantage, which is advantage of gas turbine over IC engine, is that in gas turbine, the mechanism is relatively simple. Simple mechanism we can observe, because both compression is taking place at one position, expansion is taking place at other position. Therefore, the mechanism becomes simple. Whereas in case of internal combustion engine, both the processes are taking place at the same location. Therefore, the mechanism is relatively complex in case of IC engine. The second point, the second advantage basically of the gas turbine over IC engine is that we can the balancing of the gas turbine is relatively easy compared to IC engine, because of the same reason which we have discussed above, because both compression and expansion are taking place at different locations, so we can easily quantify what amount of forces are acting at the compression side and what amount of forces are acting on the turbine side, so we can easily balance them. Whereas in case of ice engine, we cannot easily quantify the forces which we acting on the ice engine, and thus their balancing becomes a relatively difficult task. The Now we will discuss about the what are the disadvantages. The one of the major disadvantages of gas turbine over IC engine is that the network output of gas turbines. I will write gas turbine GT only. Is it okay for you all?
Yes, sir. Continue, sir.
Okay. So the network output of gas turbine than uh, is lower than IC engines. The reason the main reason for is this, because in gas turbines we are dealing with gases, so the network output for the gases, in case of compression, it is written by Bg into difference of pressure minus. So this term is not at all small, because Vg is much greater than in case of compressors. Therefore, the network output, which is the difference of the turbine work minus compression work. So here it is compressor work is relatively higher, so the network output decreases because Wc is higher. Therefore, the network output decreases. Is it okay for you all till now?
Yes, sir.
Okay. I'm only telling these small things is just to glance you difference, to give you a brief difference between the external combustion and internal combustion engine. I will not go deep into it. Now we'll directly start to our main topic, that is the different type of gas turbines which are generally in operation. So there are basically two types of gas turbines. There are basically two types of gas turbine. First one is the open cycle gas turbine, and second one is the closed cycle gas turbine. So the main difference between the open cycle and closed cycle gas turbine is that in case of open cycle gas turbine, every time we use a fresh charge. I'll show you the process. Show you. So from process will start from here. That will be our point one, and then this will be our point two. This is our compressor. Actually, my handwriting is not at all good because I am operating first time this pen. This is our compressor. This is our turbine. This will be our output. This is our turbine, and this is our combustion chamber. Okay, so this will be our point one. This will be our point two. This will be our point three, and this will be our yeah, point four. Okay, so from here first we will at point one we will start the process, and here we will enter a fresh charge. The charge will be air at atmospheric pressure. So first the charge will enter the compressor, and the compressor will then compress the air. Because of the compression, what will happen? Can you tell because of the compression what will happen?
High pressure will rise and temperature also rise.
Okay. And what happens to the volume?
Volume decreases.
Okay. Yeah, that guy is right. Uh, because of the compressor will compress the air, and because of that, the temperature and pressure will rise, and volume will decrease. So uh, we can draw the PV diagram for that. That is pressure. That is volume. So for process one, what will happen? It will look like that. That will be point one, point two. Because of the compression, your pressure will increase. Simultaneously, temperature will increase. But what will happen? The volume will decrease. Therefore, from point one to point two, the volume is lesser. Here you can see dash you can draw. Okay. Now from the process here during the process 1 to 2, what we will call it
Reversible adiabatic compressions.
yeah, process 1 to 2, what we call reversible adiabatic compression also, reversible adiabatic condition. There is another name called
Isentropic compression.
yeah, isentropic compression will happen here. Now from process 2 to 3, what will happen here? From process 2 to 3, because here we are heating this inside the compression chamber, we are heating this supplying the heat to this compressed air. So because of the heat addition, what will happen? We are supplying the heat at constant pressure, we are applying here in this combustion chamber. So since the pressure is constant and we are supplying the heat, so what will happen?
Temperature will increase.
Yeah. So here This is a straight line. This is a straight line actually. This is a point 3, and volume will also increase. Okay. So what will happen here? Heat addition will take place at constant pressure. Heat addition will take place. Okay. Now from process 3 to 4, what will happen here? Because we are having turbine, so here expansion of the that high temperature air will enter to the turbine, and their expansion of that air will take place. Because of the expansion, what will happen? Turbine will do the work, and what will happen? Can you tell?
Volume volume increases,
Yeah,
pressure decreases.
yeah, okay, you are right. So this will only happen from here, point 3 to 4. Again, curve will look like this, and point 4 we will get. So pressure here, what we this process, what we call that?
Isentropic expansion
Yeah,
in turbine.
yeah. You are right. Process 3 to 4 we call that isentropic expansion process. So this is for open cycle gas turbine. If the process will be a closed cycle gas turbine, then what will happen? Heat, a sink will also be provided, where heat from that exhaust gases which is coming from turbine will leave the turbine, will reject their heat, and they will again come to position 1. So this uh, this will happen. So from here, heat addition also takes place. Process 4 to 1, constant pressure, heat rejection will take place in case of heat rejection. Okay. So for the open cycle gas turbine, only these three process will happen. But for the closed cycle gas turbine, all these process will take place. All four process will take. Is it okay for you? Hello.
Yes, sir. Yes, sir.
Okay. Okay. Now can now what will be? This is our PV diagram. If we want to draw the TS diagram, so how will the TS diagram will look like? Wait, I'll also mark the arrows. Otherwise, you will. This is the arrow. Process will look like this. If we want to draw the TS diagram, temperature versus entropy diagram. So how will the diagram will look like? Because first from 1 to 2, isentropic compression is taking place. So wait, I'll mark that also. This is temperature. This is entropy. TS diagram. Since from 1 to 2, isentropic compression is taking place. Because isentropic process, in isentropic process, what happens? The entropy remains the same. So from process 1 to 2, what the diagram will look like?
Straight line.
A straight line. So it will be a straight line. Okay. And from 2 to 3, what is happening? Heat addition is taking place at a constant pressure. Okay. So because of heat addition, temperature is increasing. That's why our curve will uh, our curve will be increasing. Okay. Now again from uh, this will be from point 1, point 2, this will be point 3, and from point 3 to point 4 isentropic expansion is taking place. So because of the expansion, what will happen? The pressure will go down again. So pressure will again go down, and pressure will go down, and also the temperature will go down, because fluid is now transferring the that work is being done by the turbine. Because of that, fluid is expanding, and the temperature and pressure is dropping down. Okay. Now from 4 to 1, because of the heat rejection, again the process will come back to its original position, and pressure will and it regains its original condition. One, two, four. So what this process is called? This gas turbine works on a process called Brayton cycle. Okay. So in Brayton cycle, the heat addition and rejection both occurs at constant pressure. Okay. Hello.
Yes, sir. Sir, but Joule cycle means both
Yeah.
are same.
Hello.
Yes, sir.
What are you saying?
Joule cycle also called a Brayton cycle.
Mm, no. Joule cycle is not called a Brayton cycle. In Brayton cycle, heat rejection and addition and rejection takes place at constant pressure. But the other two processes are isentropic process. Na? That's why in this two process, two of the heat and we basically describe the process on the basis of rejection and addition of heat. So in Brayton cycle, heat addition and rejection both are occurring at constant pressure. That's why we call it as a Brayton cycle. Also, because it consists of two isentropic process. One is compression and one is expansion. So it will consist of two isentropic and two constant pressure cycle processes. Is it okay for you?
Okay, sir.
Okay. Now we will directly go to the numerical part with some derivation and all those part, because those are of prime importance. This is only some basic knowledge of the gas turbine which you need to go through to start the topic. Okay, now we will start directly. Uh, now we Okay, so I will first write the some terminologies like the what is back work ratio. Like these are very important. We will discuss after this what they are called. So first term, which is very important in this power plant, is back work ratio for gas turbine. back work ratio. So what is the back work ratio? Back work ratio is basically the ratio of the negative work to the positive work. So what is that negative work? So negative work is basically, in case of gas turbine, is the compression work, because what we want, what is our output is to get maximum net work. The higher the network will be, higher we will get the efficiency. So in case of gas turbine, the negative work, that is compression work, is very high. uh, that's why the network output decreases therefore in case of gas turbine or Brayton cycle. Gas turbine works on Brayton cycle only, which I have told you. So, in case of gas turbine, the normally the back work ratio, it is give the short form you can use for this is RBW. You can back work ratio. Okay, so normally in case of gas turbine, it is 40 to 60%. The back work ratio is okay. So basically, what it is, a ratio of RBW, you can write as compressor work upon turbine work. I am using WCS for compression work, but I'll write compressor work WP turbine work. Okay, so it is basically the use ratio of the unwanted work to the useful work which we want. And turbine work is our useful work, and compression work is the we want minimum, so that network output can be improved. Okay, hello.
Ah, yes, sir.
Okay,
Okay, sir. Continue.
okay. Now we'll second terminology which is important is work ratio. What is the work ratio? Work ratio is nothing, just you subtract the back work ratio. It is called the work ratio. So what is, or in other terms, we can, it is given by RW. You can write the work ratio as the net work which we want upon the turbine work. Okay, from that also you can calculate. In case of Brayton or gas turbine, this is RW is 60, 60 to 60, about 60% it is, and remaining 40% is RBW, that is 40% is a back work ratio, because this is unwanted work which we don't want, and this is the net work which we wanted. Okay,
Okay, sir.
okay. Now we will directly go to the efficiency. How to calculate the efficiency? Uh, Simple gas turbine. You can say that Brayton cycle. Okay. So can you tell me what efficiency? What is the efficiency? Because it is the output upon the input. Okay. So what is the output and what is the input? Can anyone tell me?
W net is the output.
Okay. Okay. Work net is our output, and what is our input?
It's applied to the combustion chambers.
Okay. So can we write this also as 1 minus heat rejected upon heat supplied? Hello.
Yes, sir.
You have
Yes.
already read the thermodynamics, no?
Ah, yes, sir.
Yeah. So we can write efficiency like that also, no?
Yes, sir.
Okay. So what is our QR from the cycle? I'm telling you. Tell from here. What is our that heat rejected?
M into CP in T4 minus T1.
T4 minus T1. Yeah.
T1.
Okay. Okay. Right. So we what we can write heat rejected H4 minus H1. What is the H? H is enthalpy. Okay. So H enthalpy. How can we write? Cp into T
Yes, delta.
per unit mass. For per unit mass, we can write Cp into T.
Yes, sir.
Okay. So for here, how what will be the H4 Cp into T4 minus Cp into T1. Okay. Similarly, Qs heat addition is taking place. What is the heat addition taking place here?
T3 and T2.
Okay, you are right. Heat
H3
addition,
minus H2
yeah, S3 minus S2. So here also we can write Cp into T3 minus Cp into T2.
minus T2.
Is it okay for you till now? Uh,
Yes, sir.
okay. Then enthalpy, how what we can write? 1 minus Cp. I am taking Cp common into T4 minus T1 divided by Cp into T3 minus T2. Okay. Cp we can cut directly. Hello.
Yes, sir.
So have you noted down if anyone want
Aye.
to
Yes, sir.
if anyone want to note down, I can stop here, or should I continue? Hello.
Continues.
Okay.
Continue, sir. Noted down.
So uh, from the previous what we got T4 minus T1 divided by T3 minus T2. Okay. Uh, now can we write same expression like this? 1 minus taking out T1 here common. So here it will be T1 minus here we write taking out T2 as common T3 upon T2 minus 1. Can we write it like this also? No?
Yes, sir.
Okay. Now for from process 1 to 2 process here process 1 to 2 what was is it was isentropic compression process was so for isotropic compression process, what we can write? You
PV
have
times gamma
PV is equals to constant. You can write this now.
Yes, sir.
So same process in terms of temperature. How we can write?
T2 by T1 equal to
Yeah, P2 by T1 is
P1.
equals to
T2 by P1
P2 by P1
whole power
gamma minus 1
gamma
upon
minus
gamma.
1 by gamma.
Is that okay? Fine for you?
Yes.
Okay. So here gamma minus 1 upon gamma we can take as a constant something else so that can become easy for us. So T2 upon T1 is equals to P2 upon P1 and P2 upon P1 we can also write it as RP that is pressure ratio we can write. So we can eliminate this, we can directly write RP to the power X. Is it fine? Similarly for process 3 to 4. What is it? It is happening isentropic expansion process. So same for here we can write T3 upon T3 upon T3 upon T4 is equals to T3 upon T4 to the power gamma minus 1 upon gamma. So here also since pressure T1 is equals to T4, T1 is equals to T3 and is equals to P4. From here you can see since pressure is same for P2 and P3 and P1 and P4 it is same because they are a constant pressure process. So this we can write from there. Wait, I have written I think some wrong here.
Yes, sir. P1
Yeah,
equal to P4.
yeah. P1 is equals to P4 and P2 is
P2 equal
equals
to
to
P2.
P3.
Yes, sir.
Okay. Okay. So from this two terms, what we can get P3 upon P4 is equals to P2 upon P1. We are replacing these
X.
to the power gamma minus 1 upon gamma.
Mhm.
Okay. So what we will get P3 upon P4 is equals to what we have written previously given P2 upon P1 gamma minus 1 upon gamma and gamma minus 1 upon gamma we have taken X and P2 upon P1 is the pressure ratio which is represented by RP. Therefore, T3 upon T4 will become RP to the power X. Okay.
Yes, sir.
So don't you think this term 1 and this term both are same?
Yes, sir.
So we can equate them directly. 1 equals to 2. So what we will get? T2 upon T1 is equals to T3 upon T4. Okay. So this term we can write T1 T4 is equals to T1 T3. Okay. This is very important term. You will it will be helpful for objective exam. Okay. So how you can remember this formula? Even even odd odd. Is it okay? T2 T4 T1 T3. So even terms will come on the same side and odd terms will can come on same side. So this is how you can remember it in the
Yes, sir.
examination point of view in examination. Is it okay? Then we have got this. Now from the efficiency term, what we got that 1 minus T1 from here I am writing this term T1
T4 by T1
yeah
minus 1.
upon T2 into
T2,
T3
T2
upon
minus.
okay. So from using this expression below, since from this 2 T4 is equals to T1 T3, we can write T1 T4 upon T1 is equals to T3 upon T2. So since these two terms will becomes equal, so we can cut this also and this also. Hello.
Yes,
So
sir.
thus the efficiency will become T1 minus T2, and this we can further write as 1 minus 1 upon T2 upon T1. And what is T2 upon T1?
RP power gamma
Yeah,
minus 1.
yeah, that is right. So 1 minus Rp to the power gamma minus 1 upon gamma. So this is the efficiency for the Brayton cycle or for gas turbine. Okay, it is very important for your exam. This formula you have to directly remember this formula. Now what we have got the expression here, efficiency is equals to 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. Therefore, what we get here, that efficiency is a efficiency of Brayton cycle is a function of temperature or pressure ratio only. So this question they can directly ask in your exam, that efficiency for a gas turbine or Brayton cycle is a function of temperature. They can give you four options directly here. First, efficiency. Uh, Same question will be same. Is a function of what? Wait, I'll write you question here, because in I think 2016 or 17 they asked one question like this only. Efficiency of their they give like, yeah, they ask some thermodynamics question in that, and they ask that it is a function of what. So similarly they can ask for Brayton cycle also, that the efficiency of Brayton cycle is a function of, and it can be of only one mark they can ask directly, function of first temperature only, second pressure ratio only, third temperature and pressure both, D none of these. So like this they can ask the question. So in that case, if you will remember the formula, you can directly take this answer. It is a function of pressure ratio only, because here we have derived this formula na, that efficiency is inversely proportional to this. Hello, hello.
Yes,
Yes,
sir.
sir.
Yeah, no, there is one term I actually missed. It is pressure ratio and index gamma also. Pressure ratio and gamma, because gamma is also there na. I forgot that. This gamma and pressure, it is a function of both of them. Pressure ratio and gamma index. So these two terms it depends upon. Is it okay for you? They can ask one mark question on this, because it is they have previously also asked one or two question on this type of questions. So you have to remember this part. Now now, what will happen to the efficiency? Effect on efficiency if we will change the pressure ratio, and in second case if we will change the gamma. Okay, so if you tell me what will be the effect if we will change the pressure ratio, what will be the effect on the efficiency of the Brayton cycle? Hello.
Increasing the pressure ratio increases the efficiency.
Yeah, you are right, because pressure ratio is given by this efficiency is given by this formula. So if rp will increase, if we will increase the rp, then what will happen? This whole term, if gamma is constant, that is 1.4, then if we are increasing the rp, so this whole term will increase, and when this whole term will increase, then this term will decrease, and because since this is inversely na, so this whole term will decrease, and because of this efficiency will increase. And what will happen if gamma, if we will increase the gamma index? Hello. Hello.
Yes, sir.
Efficiency decrease.
No, if both if we will increase gamma, wait, I'll show you. If we will increase the gamma, so we can write this term as like this na, 1 upon rp to the power 1 minus 1 upon gamma. Is it okay? So if we will increase the gamma na, so what will happen if we will increase the gamma? This term will automatically decreases. This term will decrease, because this term will increase, this whole term will increase, and this whole term will increase, then what will happen to this term? this
Decreases.
this decreases. So because this decreases, the 1 minus that is decreased value, so what we will get? Efficiency will increase. So with both increase of pressure ratio and the index, the efficiency of the Brayton cycle tends to increase. Is it okay for you? Hello.
Yes, sir.
Okay, now
Sir,
yeah,
diabetic index increase.
yeah,
What happens if diabetic index is increased?
yeah.
Its efficiency decrease, sir.
No, no, it will increase. Here I have shown you now. See here. If index will increase, so what will happen? Index will increase. This term will decrease. Whole term will decrease. So this, if this term will decrease, then what will happen? This term will increase. Then 1 minus is a decreased term, na? So it will increase. So because this will be higher, because this is lower, this 1 minus term will be higher, and then because of this rp will increase. rp will increase, then this whole term tends to decrease and efficiency improves. Hello.
Okay, okay, sir.
Okay, now we will directly go to one or two more topics. Then we will discuss the numerical part, because that is of more importance in the exam. They will ask only the questions from the theory section which they can ask. I have already told you. Now the another question, another derivation which is of important to you is the what is will be the optimum pressure ratio for the maximum work output, because ultimately we want to uh, work output to be higher, so that efficiency can be higher. So what will be the rp, that is pressure ratio, uh, optimum for maximum work output? This you can also call the optimum pressure ratio. Okay, so uh, what uh, what is the net work output which we can write from? Tell me from this cycle. What will be the work output? Hello.
CP T3 minus T4.
Yeah, T3 minus, yeah, CP T3 minus T4 minus,
CP T2 minus T1.
yeah, that's right. It is a, what is the work net? Work net we can write as turbine work minus compressor work. Okay, so turbine work is what? It is from 3 to 4. So CP, we can write S3 minus H4. Okay, which we can further write CP into T3 minus T4, and compressor work is H2 minus H1, which we can write Cp into T2 minus T1. Is it okay for you till now?
Yes, sir.
Okay, so network output, how we can write then? Uh, we can write S3 minus H4 minus H2 minus H1. Okay, which we can further write Cp into T3 minus T4 minus Cp into T2 minus T1. Okay, so Cp we will take common, and T3 minus T4 minus T2 plus T1. Okay, is it okay for you?
Yes, sir.
Okay, so what is our that Brayton cycle looks like on a TS curve? This is temperature, this is entropy. It looks like this. Okay, one, two, three, and this is the fourth. Actually, it has to stop here, but it got extended. Okay, so the maximum temperature here, what it is the maximum temperature? It is T3. The minimum temperature is T1. Okay,
T1.
so we can write T1 is equals to T minimum and T3 is equals to T max. Okay, also from the previous term, what we got, T1, T3 is equals to T2, T4, which I said you can remember as T1, even, odd, odd. Okay, so from here, what we can write? From here, we can write, we can replace any one of term. Na? T2, we can write T2 is equals to T1, T3 upon T4. Can we write this?
Yes,
Hello.
sir.
Now we will put this one here in place of this. Okay, in this T2, we will replace this T2. Put this T2 value over there. Okay. So what we will get here? Work net is equals to
CP
CP
T3 minus T4
CP T3 minus T4 minus,
T1 T3 by T4
yeah,
plus T1.
plus T1. Is it okay? Now for maximum work output, what we want? For maximum work output, or maximum, someone messaging. I thought someone is messaging. For so for maximum work output. What we want for maximum work output? From here, for maximum work output, what we want, turbine work should be higher. Turbine work should be higher and compression work should be lower. So for higher turbine work, higher the turbine work would be, higher will be the net work output. Is it okay?
Yes, sir.
Okay. So for more turbine work, what we want? What we want that temperature T4 should be lower and lower.
Yes, sir.
Okay. So temperature T4, the lower it goes, the maximum the turbine work we will get. So for uh, so can we differentiate the network for finding out the maxima or minima? What we do, we differentiate the term with respect to what we want to get the maxima and minima. Therefore, here what we want the work output to be maximum. So for maximum work output, the temperature T4 should be lower. Therefore, we will differentiate this with T4 and equate to 0 to get the maxima or minima. Is it okay? Hello.
Yes,
Yes,
sir.
sir.
Okay, so when we will differentiate it, what we will get the final term? Can anyone tell me differentiating network out with respect to temperature T4?
T4 is equal to root of T1 into T3.
Yeah. So after differentiating network with respect to T4, what we will get here? We will get -1 plus T1 T3 upon T4 to the whole square is equals to 0. From that we can write T1 T3 upon T4 the whole square is equals to 1. So T4 will become the root of T1 T3. Okay. Hello.
Yes, sir.
Is it okay? Now from here, for a ideal Brayton cycle, for an ideal Brayton cycle, what we want here, cycle looks like this. We want that this temperature and this temperature T2 should be equals to T4. This would be our T3 maximum and this should be our T1 minimum. For ideal Brayton cycle, we want T2 is should be equals to T4. Okay. So from here we can get that T2 also is equals to under root T1 T3. Okay. So these two terms are very important. You should mark them important because when we will solve the numericals, it will help you out. Okay. Hello. Hello.
Yes, sir.
Is it okay till now?
Yes, sir.
Okay.
So T2 is equal to T4. We should remember it
Yeah, for ideal Brayton cycle,
for ideal Brayton cycle
yeah,
only.
for ideal Brayton cycle, we want that T2 should be equal to T4.
Okay.
For this is a ideal Brayton cycle, we is assuming for that the maximum work output. So maximum output we will only get when T2 will be equal to T4. Okay.
Okay, sir.
Now, since we have got T2 is equals to T4 is equals to under root T1 T3. Now network we can write maximum work output. Uh, network output maximum work output. So W max we can write is equals to Cp to P3 minus, what was the previous? T3 minus
P4 minus
P4.
T3 T3 minus
P4
T4 minus T
P1
minus T2
P3.
plus T1.
Yes, sir.
Is it okay? Now Cp T3 minus, what is T4? T4 is under root T1 T3 minus T2. No, T2 it is also as T1. Okay, it will become Cp 2 3 plus 1 minus 2 times of T3. Okay, which can further be Cp we can write under root T3 whole square we can write plus T1 we can write under T1 whole square minus 2 into under root T1 T3. Is it fine for you? Have you got how I have written this
Yes,
T3?
sir.
Okay. So maximum work output what we will get Cp into T3 minus under root T1 whole square. Is it okay?
Yes.
Yes.
Okay. Now the corresponding to this maximum work, what will be the optimum pressure ratio? Pressure ratio we were written up previously. What it is called? Rp is equals to P2 upon T1, which can further be written as P2 upon P1 to the power gamma minus 1 upon gamma. Okay. Hello.
Yes, sir.
Yes.
Okay. So can we write this term as P2 upon P1 is equals to T2 upon T1 to the power gamma divided by gamma minus 1? Can we write it like this? We have
Yes, sir.
just changed the indexes. Now, from this above, what we have got T2 is equals to under root of T1 into T3. So this we will put here. Okay. So what we will get P2 upon P1 is equals to under root T1 upon T3 upon T1 to the power gamma minus 1 upon gamma. Have you got this till that?
Yes, sir.
Okay. So Rp optimum or P2 on P1 can further be written as, from previous time I am already on P1 the power gamma divided by gamma minus 1. So P2 upon P1 is equals to under root P3 divided by under root P1 to the power gamma upon gamma minus 1 is equals to, can we write it like this? P3 upon P1 is equals to gamma upon 2 gamma minus 1. Can we write it like this? Because it is under root, so we can put half instead of that. Hello?
Yes, sir. Yes, sir.
Okay. Now for the ideal Brayton cycle for maximum work output, what we have assumed that uh, what we have assumed,
T2 is equal to T4.
yeah. So RP, wait. So RP or one can be written like this. Two or CRP remember. So for this, hello.
Yes, sir.
Okay. Now last topic we will discuss. After that, we can solve the numerical part. So, you all have studied the thermodynamics, no? So, can you tell me what is the isentropic efficiency? Uh, Hello, hello.
It is the efficiency, it's the ratio of the efficiency when entropy is same and to the real cycle.
Okay, uh, you are right. So, isentropic efficiency. Just remember efficiency. What is efficiency? In exam, no one is going to ask you what is isentropic or something. So, what is any efficiency called? Efficiency is basically you can say that small upon big because it should always be lower than one. Na? Hello.
Yes, sir.
Okay. So something small will be above and big term will be lower, will be in the denominator, and efficiency is always less than one. So remember that this term. Okay. So in case of compressor, wait, I'll show you the cycle first. Temperature, entropy. So this is the cycle. This is same. E3, 1, 4. Okay. So what exactly happens? Because in, for the problems point of view, we assume that process 1 to 2 is isentropic process, but in actual condition no process is isentropic. Therefore every time there is a difference. So in the compressor side also you will get the enthalpy H1 and H2 1 and 2, the entropy is not at all same. So there is a difference between the at point 2 and 2 dash. Similarly, here also the entropy at the turbine side is also different. Here is 4 is 4 dash. So because the in real life the entropy is not same in actual condition. Therefore, for to compensate for that, we are taking the isentropic efficiency for on the compressor side and on the turbine side. Okay, so on the compression side, how we can write efficiency of isentropic efficiency of compressor? I am writing like this. So I have told you it is something small upon big, come upon jada. You can say that. So uh, what it is? Which term is smaller and which term is bigger? Can anyone tell me?
2 to 1 is smaller.
Okay, so wait, I'll show you one efficiency also. Isentropic efficiency, its actual definition is uh, uh, actual for compression and turbine both is different. So for compression case, it is the ideal small upon big, I have said no. So here smaller one is which one? H2 minus H1, and bigger one is H2 dash minus H1. Therefore, we can write it as H2 minus H1 upon H2 dash minus H1. I have written this. I have tried to explain this you in simplest possible way, because sometimes it becomes really confusing in case of compression and compressor in case of turbine, because in actual case isentropic efficiency definition tells that it is the ratio of the actual work done upon the ideal work done. Okay, but in case of turbine and both the definition becomes sometimes confusing, because that's why I have tried to explain you in terms of small and big. Hello.
Okay, sir.
Okay, so similarly in case of turbine you can write isentropic efficiency, uh, which one is smaller and which one is bigger.
T3 minus T4 gas.
Okay.
Like H3 minus H4 gas. Smaller one.
Okay, H3 minus H4 dash upon S3 minus H4. Is it okay? Hello?
Yes, sir.
Okay. So these are only mm, these are the only part which are important. This is all. This is also important. One, this compression. This is also you have to remember, because during solving numerical it will be important. Also RP optimum, I have forgot to tell you one thing, that here T3 we have in the assumption T3 is the maximum temperature na? And T1 is the minimum temperature. So we can also write R optimum as T higher minus T lower to the power gamma divided by 2 gamma minus 1. Is it okay?
Yes, sir.
Okay. So we'll try to glance you some important formula directly. Okay. So first one I told you about the back work ratio. So what is the back work ratio? It is the ratio of the compressor work upon turbine work. Okay. Second one is the uh, work ratio. It is the net work divided by the turbine work, or you can say that the RW is equals to 1 minus back work ratio. Okay. Third important formula, which is the efficiency of the Brayton cycle, or for gas turbine, which is 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. Okay. Fourth important formula, which I have told you, that even order, T1 is equals to T2. Okay. Fifth important formula, which I have told you, that for maximum work output, T2 is equals to T4 is equals to T1, T3, and maximum work. Sixth one is the maximum work output is given by Cp You can also write M because previously we were considered per kg. So if mass flow rate is also given mass, then you can multiply it and you can write under root b higher minus under root but whole is cube. Yeah. Sixth formula is the RP optimum, which is given by higher minus T lower gamma divided by 2 gamma minus 1. Seventh important formula is isentropic efficiency of compression IC, which you can write minimum upon uh, H minus H1 divided by H2 dash minus H1, and isentropic efficiency of turbine you can write H3 minus H4 dash divided by H3 minus H4. These are the seven important formula which you need to remember for the whole Brayton cycle. Hello,
Yes, sir.
is it fine?
Yes, sir.
So, what is the time right now? It's already 7:21. So, if you want, I can take more one or two numerical we can solve in this class. Hello.
Sir. Okay, sir.
Mm, Uh, uh, you don't have any class, na? After this.
No, sir.
Sir.
No,
Okay.
sir.
Okay, then we'll go with the one or two numericals. Then we'll solve numericals tomorrow also. Okay. So first question I'm going to write on the board. So first you try, then I'll tell you. I'll give you 5 or 10 minutes to solve that problem. Then first you try based on this seven formula only. That question can be solved. So first you try to solve. Then if you will not be able to, then I will try. So this question came in gate 2003. Okay, the problem is in a gas turbine. I am writing GT or in a hot combustion products having a value of Cp and Cv of 0.98 joule per kg Kelvin and 0.753 joule per kg Kelvin respectively. These charge enters turbine at a pressure of 20 bar at a temperature of 1500 Kelvin and exit turbine at pressure of 1 bar. Okay. So assuming the value of gamma is equal to 1 and isentropic efficiency of turbine. I'm writing directly IT for 94%. What is what is the actual work of turbine? Hello, hello.
Yes, sir.
Yes, sir.
Uh, can you solve this?
We'll try, sir.
Okay. Remember this actual work done. What we are talking about? Actual work done is this one. Okay. I'll give you 5 or 10 minutes. Please try. Then I'll tell you how to solve this problem.
Is it 689 kilojoule per kg?
Yes, you are right. 689 kilojoule per kg. Has anyone other got the same answer? Hello. Yeah, hello. Yes, it's 689 kilojoule per kg. It's right. Has any other one
Yes,
other guy who has got the same answer?
yes, sir.
Okay. Mm. I'll tell you the procedure how you can solve this problem. So here we have given isentropic efficiency for turbine. So here we can write draw like this. And the process become H4 type. So what we have to write, find out actual work output. So previously actual work output was S3 minus S4, but because isentropic efficiency is given, so the actual work output will change from S3 minus H4 to S3 minus H4 dash. Okay, so what we are about, what we have to find is work output for actual for turbine. This we have to find. Okay, so what is given in the question? Pressure of it enters at a pressure of 20 bar and it leaves the turbine at 1 bar. Okay, so T3 it enters at point 0.3 and it rejects at point 0.4 at a pressure of 1 bar. Okay, so temperature for T3 it is given. What it is given? 1500 Kelvin in the question. Okay, also the value of gamma is given, that is 1.3. The value of Cp and Cv is given for that enthalpy calculation they have given. Cp what they have mentioned, 0.98 kilojoule per kg Kelvin. Okay, and also isentropic efficiency of turbine they have given 94%. So first, what will be the actual work? Previously, actual work for turbine is equals to S3 minus H4 dash. Okay, it will be actual work which we have to find, and for that, what we have to find, this temperature T4 need to find, because T4 dash has to be find, because T3 we are already having. So what we will get, Cp into T3 minus T4 dash. Okay, so Cp is given 0.98, T3 1500 Kelvin minus T4 dash. For finding the T4 dash, no, this for finding T4, what we have to do first? Isentropic efficiency of turbine is given. What is the isentropic efficiency of turbine, which we have previously uh, determined that it is H3 minus H4 dash divided by S3 minus H4. Okay, so which can also be further written as Cp into T3 minus T4 dash upon Cp T3 minus T4. Okay, so of turbine it is given 0.94, 94% can be written as 0.94. Cp will cut out each other. Okay, so 0.94 is equals to T3 is given 1500 Kelvin minus T4 dash. Okay, and T3 is again given minus T4. Okay, so first we have to determine T4, and from T4, putting T4 value here, we can find T4 dash. Okay, so since process 3 to 4 process 3 to 4 is a reverse isentropic process. This process 3 to 4 is isentropic expansion. Therefore, we can write for process into 4 T3 upon T4 is equals to T3 upon T1 to the power gamma 1 is 1 upon gamma because it is the pressure ratio. Okay, so pressure of we have previously discussed P2 is equals to P3, P1 here we have to write P4, so P4 is equals to P1, so T3 upon T1 is equals to becomes P2 upon P1 to the power gamma is also given 1.3, so 1 so 1 so 1.3 minus 1 on 1.3, so P2 P2 is 20 bar, P2 and P3 are same, that is 20 bar, so 20 divided by 1, so 0.3 upon 1.3. Okay, also T3 temperature is given 1500 Kelvin upon T4 is equals to 20 to the power 0.3 upon 1.3. Okay, from here by putting our value in that equation, we can find T4. T4 will be equal to 751 Kelvin. Who has got this 751 Kelvin? Hello?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. Then we can put this value, that isentropic efficiency formula. What was that previously we have given this 0.94 in this T4 term we can temperature of T4 we will put here, we will get T4 dash here, so 0.94 is equals to 1500 minus T4 dash divided by 1500 minus 751. Okay, so what is the T4 temperature you have got, can anyone tell me?
796 Kelvin.
Okay, so this is the so the actual work done, work actual for turbine is equals to 0.98. We will write again Cp into T3 minus T dash 0.98 into 1500 minus 796 Kelvin. So what we will get? The units you have to remember, kilojoule per kg Kelvin into Kelvin. Here it is Kelvin, so Kelvin cut out. So finally unit we will get this one. So what will be our answer? 689 kilojoule per kg. Is it okay?
Yes, sir.
Okay. Uh, hello.
Yes, sir.
Can we discuss more questions tomorrow on Saturday? Because Saturday also we are having class. Because right now I have to leave somewhere. Hello.
Okay, sir. Sir, next class is on Saturday, sir.
Yeah, Saturday. You might have got that schedule, na?
In that 7 to 8, it is showing casting.
No, no. It is from 6 to 7 only. 6 to 7. Same timing from 6 to 7 on Saturday. Casting
It's
is
not on
hello.
Saturday. It is not showing, sir. 6 to 7.
So at what time it is showing actually? Wait, I'll see again.
On 10th December and
Saturday.
7th.
No, Saturday is there is no class now. Saturday I am taking from 6 to 7 only. Here I have mentioned another slot is on December 10th on Saturday. So we'll be taking on Saturday from 6 to 7. 7 to 8, it is casting and design joining classes. Hello?
Okay, sir. 6 to 7.
Yeah, 6 to 7 we can have.
Okay,
So
sir.
in that class we'll solve the more problems on this topic, and then we'll move on to some more topic like regeneration of gas turbine and all those topics.
Okay, sir.
Okay. So is there any doubt, anyone of if anyone has
Sir,
doubt? Yeah,
constant volume gas turbine is works of the Atkinson cycle, sir.
yeah.
Constant volume gas turbine, sir.
Constant volume gas turbine. No, no, no. There is gas turbine doesn't work on constant volume. It only works on that constant pressure cycle.
Atkinson cycle is means, sir.
Which cycle?
Atkinson cycle, sir. AKTION.
Yeah, it is a cycle, but it is not in our syllabus, so we will not study that. You have to just remember the Brayton cycle. It,
Uh,
that is in ESE syllabus.
that cycle not in grade syllabus, sir.
Yeah, that is not in the GATE syllabus actually. That's why I haven't discussed about that. The Brayton cycle is there in our syllabus, so that's why we are only talking about that. Erickson, the cycle you are talking about, it is in ESE syllabus, Engineering Services Examination syllabus.
Okay, sir. That cycle is why not practically used, sir.
What?
The Atkinson cycle is not used practically most of times.
Hmm, better you skip this part because exam is near. So focus on the topics which we are teaching in the class. Hello.
Okay, okay, sir.
Because I can tell you, but it will be of no use for you right now because you're already having so much syllabus to study. So
Okay, okay, sir.
so better to focus on these topics which we are discussing because uh, it will these are also so big topics. So better to remember the cycles which are there in your syllabus, not these cycles which are out not in your syllabus. Like
Okay,
you should remember auto cycle, diesel cycle, dual cycle, Brayton cycle, all those cycle you should remember.
okay, sir.
Yeah. So any other doubt for today's topic? Hello.
No doubt, sir.
Okay. Tomorrow on Saturday 6 to 7 we'll solve some more problems on the same topic. Okay.
Okay,
Okay,
sir.
And on Wednesday, since you are not having any class from 7 to 8, so we can extend a class for half an hour or 1 hour if you want.
okay, sir.
Okay.
Okay, sir.
Okay. Then we'll meet on Saturday. Uh, on Saturday, we'll do some problems on this, the formula, which 7 formulas we have told. And next, we'll talk about the regeneration, reheating, and all those in the gas turbine. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Okay.
Thank you.
Okay.